Welcome to Module 6. Module 6 is dedicated to mass spectrometry as a detection technique following chromatographic separation either by gas or liquid chromatography. The learning objectives of this module are to understand the principles of mass spectrometry as a measurement technique, to understand the components of the system itself, the mass spectrometer, and the parameters that influence the results. The focus will be placed on a selection of parameters that are key elements of food safety methods. Finally, we will review a number of official methods for food contaminants with the objective to understand why mass spectrometry, both single quadrupole and tandem quadrupole, have become so important for the food safety laboratory. Section 1. Introduction to mass spectrometry. Mass spectrometry is a technique that uses mass. However, there would be no measurement possible if the molecule of interest was not charged or in ionic form. So in reality, it's a measurement driven by mass to charge ratio. The instrument used for mass spectrometry is called a mass spectrometer. We briefly introduced the principles in modules 4 and 5. There are three main components in the mass spectrometer. The ion source is where the solution containing the mixture of chemicals extracted from the matrix is introduced into the instrument and molecules of interest are charged. The mass analyzer is the heart of the instrument, where the selection of ions is made by way of a movement of ions driven by a combination of electromagnetic current and radio waves. We will discuss different implementations of this system that provide certain advantages for the detection and quantitation of different types of chemicals in different concentrations. Finally, a simple detector that counts particles without any type of selectivity is present at the end of the process to count whatever reaches it. While the technology to achieve this process is very advanced and was only made possible by developments in electronics, fluid mechanics, and software components, the principles behind it are quite straightforward. As mentioned before, the source is where the solution, or the gas stream coming out of the GC, enters the mass spectrometer and chemicals of interest are ionized or charged either negatively or positively. It is important to remember that without charge, there would be no mass spectrometry, and while it looks simplistic, this formula reminds us. We will discuss this again when troubleshooting methods in our in-person training. There are different types of ion sources available, and the selection of the appropriate one depends on the sample, the components we're trying to measure, and also the concentration at which they are present. The first group of sources is based on atmospheric pressure ionization, API. As the name indicates, this type of source operates at atmospheric pressure, which offers the advantage of avoiding a vacuum pump at this stage, making it a simpler system. The most popular type of API is electrospray ionization, or ESI, while atmospheric pressure chemical ionization offers some advantages for chemicals that are not easily charged. Matrix-assisted laser desorption ionization, MALDI, is a technique that uses a laser beam to lift chemicals from a solid surface and produce ions. Finally, electron ionization, EI, is based on the use of an electron beam to cause ionization. Let us review these techniques in some more details. Electrospray ionization, ESI, is essentially a system where the sample solution is sprayed through a heated tube to which an electrical voltage is applied and surrounded by a stream of inert gas, usually nitrogen. As the solution approaches the tip of the capillary tube, its temperature increases, and when it leaves the tip, the spray effect, combined with the heat and the gas stream, cause the formation of small droplets that immediately start to dry. The voltage applied at the tip of the capillary tube causes the droplets to be charged. As the droplets proceed through the empty space between the source and the entrance of the mass analyzer, they go through more loss of the solution solvent and split up into smaller droplets. Ideally, they become completely dry, which leaves ions in gas phase to enter the mass analyzer. The critical steps of this process are the addition of a charge to the droplets, whether negative or positive, fission into smaller droplets, and evaporation of the sample's solvent. If any of these steps doesn't happen, there will be no ions entering the mass analyzer. Similarly, if any of these steps is only partially achieved, only a fraction of the expected quantity of ions will enter the mass analyzer. ESI can be used to create positively or negatively charged ions. When hydrogen is added to create a +1 charge, it creates what we call a molecular ion. A molecular ion can be positively or negatively charged, but the characteristic is that it is the original molecular weight of the compound of interest plus or minus 1 mass unit. When sodium or ammonia ions are added to a molecule to cause it to become positively charged, we call the product of this addition an adduct. Adducts, therefore, weigh the sum of the molecular masses of the original compound and the added compound plus or minus 1. Adducts are extremely important for confirmation of identity when using a single quadrupole mass spectrometer. This will be discussed further during our practical laboratory sessions. When MSMS is available, we favor the use of the molecular ion since these are more specific and we have the ability to create other elements for the confirmation of identity using the second mass spectrometer. We will discuss this further in the upcoming section on the mass analyzer. The figure in this slide shows one example of the creation of a molecular ion for carbendazime through the addition of a hydrogen, which creates a charge of +1 and a molecular weight equal to carbendazime +1. Carbendazime is a pesticide contained in the official method discussed in section 3 of this module. The same principle of action is used to create negatively charged molecules in negative electrospray ionization. In this case, the conditions favor the removal of a proton, which causes the resulting ion to be negatively charged. Similarly to positive electrospray, we favor the formation of the negative molecular ion in tandem quadrupole MS, and adducts when needing a confirmation of identity using a single MS. Chemical compounds are by their nature better suited for positive or negative electrospray ionization. Basic compounds more easily form positive molecular ions, while acidic compounds more readily form negative molecular ions. Modern mass spectrometry systems have the ability to switch between negative and positive electrospray ionization within the same run. This is an important advantage in food safety, where we are often working to quantify large numbers of contaminants at once, and it enables more compounds to be included in the same method. In other words, we obtain more results for the same analysis, which saves time and money. Sample preparation must always match the type of source we intend to use on our instrumentation. In the case of mass spectrometry used as a detector following chromatography separation, we have to ensure that the eluent from the chromatography column is compatible with the ESI and with the positive and or negative charge that we want on the compounds of interest. Generally, ESI works best with solutions that have a high organic content. For example, it works best with a high acetonitrile or methanol content in HPLC. However, we need to have at least some aqueous phase with a modifier, such as acid or ammonia, because we need a source for the H plus or OH minus that give or take the charge to form a molecular ion. Typical acids that promote ionization in positive mode are acetic and formic acid, while ammonia is a usual modifier for ESI in negative mode. It's important to note that these modifiers serve a function of helping the ionization, but they must also help, or at least not hinder, the chromatography separation that precedes mass spectrometry. Other modifiers are available and useful in various applications, but for the new analysts in the food safety laboratory, remembering these three will help understand most of the relevant methods. This schematic from the Waters Corporation shows the position and the actual shape of the different parts of the ESI source. The capillary tube is seen on the right, where an orange stream of sample is sprayed and forms the usual cone seen from a spray nozzle. The yellow stream represents the droplets that become small enough through the drying process called desolvation, aided by the nitrogen gas flow and the high temperature, to be attracted by the vacuum coming from the cone located in the middle of the diagram. This angled design ensures that large droplets that still contain a lot of solvent do not enter the mass analyzer, which can only move gases through the quadrupoles. The wet stream will simply land on the floor of the source. We will look at this source chamber in the practical laboratory portion of this course. At this time, we will start introducing some reasons for failed measurements, or in other words, discuss troubleshooting poor results. An example of a poor result that could be due to a problem in the source is a very low signal intensity. Looking back at the critical steps of the ESI process, we will discuss how an inadequate solvent composition at the outlet of the HPLC, or a low temperature, or a wrong voltage at the tip of the capillary tube, or a wrong angle between the capillary and the inlet cone, could all result in few or no ions making it into the mass analyzer. The ESI source is used for pesticide residues, veterinary drug residues, mycotoxins, and many other food contaminants analyzed by LC-MS. As such, it is by far the most common source in the food safety laboratory.